Okay, so today we're going to work on, we're still on the unit of kinematics, but today we're going to work on vector quantities of kinematics. So these are really what we described kinematics as was just a description of motion, but really how motion is occurring, not why it's occurring, right? So dynamics is more of the study of why motion is occurring. And usually when you're looking at motion, everything just boils down to forces. Okay, that's usually the why of why that motion is occurring. But for our intents purposes, we're just going to look at descriptions of motions, and specifically those descriptions of motion will involve certain vector quantities, which we will be talking about in this lecture, which is going to include position, displacement, velocity, acceleration. Okay, so that's just kind of a preview. I know you have had some previous exposure to this, but once again, you have to kind of ground these generic principles, okay? So like I mentioned, kinematics is basically the description of how motion occurs, and we're going to look at that description through position, displacement, velocity, and acceleration. We're going to start with position, but once again, like we talked about before, all of these are vector quantities, and any vector quantity is basically anything that has a magnitude and a direction, okay? So most commonly, position is denoted as d with the vector sign. Okay, so we'll call this vector d, right? And just to do a little recap from last time, guys, if you wanted to calculate the magnitude of the position vector, you can write it like this, or you can write it like that. Okay, so it's really up to you. This just implies that you're only looking at the magnitude of the vector. But if you write the vector like this, you're going to have to look at the direction and magnitude. All right, so an example of this is, let's say Bob was positioned 10 meters north, let's say relative to his house. Okay, so you always have to look at position in terms of some kind of reference point, right? And you may have seen potential graphs associated with that. But really what 10 meters north relative to his house means is, that you have to have a reference point. So his house is basically the point of origin where he started. 10 meters north is basically, there's the direction associated with it, and the 10 meters here is the scalar. Okay, so this is your vector. This is your position. Okay. And the thing about objects is that we're not only going to have a single position, specifically if the object is not at rest, right? So if the object is moving, then we're going to see changes in position. So because we're going to see changes in position, it's really important to understand the initial position and the final position, okay? Whenever we're looking at initial and final states, we look at something called a state function. And a lot of these things that we're going to be measuring are called state functions, right? So state function is basically any type of characteristic or any characteristic or really variable that is measured from its initial to final states. Okay, what I mean by that is the path is irrelevant, right? So sometimes we might consider state functions as path independent because the pathway, the way we go from initial to final is irrelevant. Here's an example. Say you're looking at measuring temperature, okay? At 9:20 a.m., you measure the temperature as being, it's 4 degrees Celsius. By 3 o'clock p.m., you measure the temperature as being 10 degrees Celsius. You don't care specifically how the temperature changes at every minute interval or every hour interval. You don't care what the temperature is at 9:40 or 9:45 or 9:43. You do care about how much the temperature has changed from the initial state to the final state. And that's essentially what a state function is. We don't care about the path, right? So position is path independent. It's a state function. But another aspect of position, the scalar aspect of position, is called distance. And distance is not a state function because it is path dependent, right? If you take a longer path or a shorter path from going from your initial point to your final path, that's going to affect your just your distance, right? So that's something that you want to kind of keep in mind. But because we're looking at state functions, for the most part, when we're considering vectors, we're just going to look at initial and final states. So we're going to use the subscript I and F to represent that, right? So position is the location of any kind of object. Now they usually say particle if you're just looking at any entity that we're measuring in physics. But a state function is basically the orientation or the location of an object in 2D or 3D space. Okay. Now, obviously, when we're looking at reality, guys, we're not looking at two-dimensional space, right? But for the most part, for what we're going to be discussing in 2D space is going to be based on these problems that we look at. Most of the times when we're looking at physics, in this course especially, we're going to just be looking at two-dimensional space, right? Now, I don't know if all of you have taken calculus, but the three-dimensional space just means that you have an extra component or an extra dimension, which is x, y, and z. Okay. For the most part, we're going to simplify it a little bit. We're just going to look at two-dimensional space, but we can use it as a really good abbreviation and a really good learning tool to kind of understand how three-dimensional space operates. Okay, so we won't overcomplicate it in that sense. So that's what position is. Displacement is the change in position, and this change usually occurs over a time interval. And displacement usually indicates that the object is moving. If an object is moving, then its position will change relative to some time interval. Okay. So displacement is a change in position during a time interval, and you can basically calculate displacement by finding the final position and subtracting by the initial position. Remember that if you look at this quantity here, guys, it is a vector. Make sure you're careful with subtracting and adding vectors. You can only add and subtract their particular components, right? So review some of the component addition we talked about. I know we only briefly looked at one example last time, but I would ask you guys to do some review regarding that. But remember that these positions, right, you can break them down into X and Y, right? And basically, this is the X component of that position. So maybe we'll actually write this as X, Y, right? So if you think about it like this, this is your vector, your final position, and you can break it down into its X component and its Y component. These are the component vectors, right? And we're writing it in this coordinate form that we talked about last time. And if you think about adding or subtracting these vectors, right, you want to look at only adding and subtracting these components, right? When you have a negative vector, guys, what that means is you're adding the negative or the opposite vector of one of the vectors. Okay, so in this case, you're taking your final displacement, or sorry, your final position vector, and you're adding the opposite vector of your initial vector. Yeah, that's what subtraction means. And think about like what that means in terms of the component addition of vectors, right? The other way you could do it, you could also draw it out using geometric vectors. That's also another reason. That's also another thing that you can do. But for the most part, I really want you guys to break down to components. That's basically what I'm looking for. It is in terms of calculation-wise, it's more accurate. It's a lot cleaner rather than sketching a bunch of triangles and using sine and cosine law. It's a lot easier for you to make a lot of mistakes that way. Okay, so I really want to focus on this component addition. So delta D here is the displacement vector. And if you want to just find the magnitude, that tells you what is the difference between the initial position and the final position. Okay, remember that this is a state function. We don't care about the path. If an object starts at point A and goes back to point A, the displacement is 0. And that doesn't mean the distance is 0, but the path is independent if you're looking at displacement, right? Because distance is path dependent, then you have to actually look at how the object moved from point A to back to point A, right? So that's what I wanted you to get from that. Really understand this notion of state function. And for the most part, we're going to be measuring a lot of state functions, okay? Distance is a total length. Like we talked about, I'm sure everyone here knows what distance is. And basically, when we're looking at measuring position and displacement, the SI unit we're using is meters. Okay, so hopefully you guys understand that, and you guys can understand the different conversions between different prefixes of meters. Okay, so that's stuff that you should just go back and review. And it's very important because these are vectors that we understand how to use the appropriate directional system. Once again, we are going to be using a quadrant bearing system. So for instance, if this was usually how they represent this on some kind of graph. The origin is usually the reference point. This is point 0, right? And let's say that the object was here, okay? And let's say that this was, 10 kilometers and this was 30 degrees, right? If you wanted to look at this, because this is not a direct, it's not a straight line, or it's not a vertical or horizontal line. If this was north, this was east, this was south, and this was west, you can figure out what each of the components are, right? Or you could say this is 10 kilometers east, 30 degrees north. Or we could say 10 kilometers north, 60 degrees east, right? Or you could find the individual components and then say, we went this many kilometers east and then we went this many kilometers north, okay? But this for the most part will suffice. So make sure you guys use the quadrant bearing system for the most part. We're not going to use true bearing systems like I mentioned last time. We're going to be using quadrant bearing system because of the fact that it is a lot more cleaner, it's more universal, it's very easy to articulate direction. Okay. All right, so most of that stuff is a little bit of review, so just go back and review that. And another type of vector quantity that we're going to be looking at is velocity. And the scalar of velocity is called speed, okay? So displacement is basically change in position, and that change in position occurs over a time interval. What is a time interval? Well, this is also a state function. And remember that state functions don't have to be vector quantities, guys. You can have scalars that are also state functions like time. So a time interval is just the final time minus the initial time. Like every other like every other state function, all state functions are basically a final condition minus the initial condition, okay? And basically, we can express velocity as a change in displacement over the change in time. This is also associated with speed, okay? We know that the average speed is basically the change in distance over time. That's what we're talking about here. Whenever you see the word average, guys, this is always basically a change between an interval, right? It's usually time. There will always be an interval, and an interval just means that there is a final position and an initial position, right? An instant, which is completely different from an interval, an instant is basically where the interval is equal to 0. So the initial position or the initial condition is equal to the final condition. Okay, so an instant is basically a single point in time. An interval is between two different regions of time. Okay, so that's something that you want to understand. Now, average speed is a scalar. There is no direction associated with this. And because it is distance over time, a time interval, distance is measured in meters, time is measured in seconds. So the unit of speed here is meters per second. Okay. Velocity is defined as a rate of change of displacement per unit time. And displacement here is a vector. So if we take a look at this equation here, right, displacement is basically the final position minus the initial position over time. And you can write this as final position minus initial position over final time minus initial time, right? Because this portion on the numerator is a vector quantity, then we can understand that velocity is a vector, right? The direction of your velocity is going to be associated with the direction of your position of your displacement vector. Okay. Now, why do I have to denote that this is average velocity, right? There's also another type of velocity called instantaneous velocity. So when we're looking at velocity, we're looking at instantaneous velocity as well as average velocity, right? And basically, The instantaneous velocity is between an instant in time, whereas the average velocity is during a time interval. In both cases, we're still going to use this formula, right? Whereas an instantaneous velocity, instead of having this formula, we're going to basically have an instant of the position over the instant of the time. Right? Now, they do represent this a different way when you're looking at calculus, but basically the instantaneous velocity, if you guys have studied calculus, you can express this as a limit where the limit of delta t approaches 0. What that's saying is that as this gets closer and closer to 0, you're going to get to the instantaneous velocity. Now, we're not going to look at calculating instantaneous anythings because of the fact that you would require some calculus for that. I can show it to you how to. I can show you how to do it graphically. Graphically, we would draw a tangent. We'll talk about this later on. Okay. So what I want you to understand is really this formula. I'm sure you've seen it before. And when the instantaneous, we can imagine that the average velocity is made up of several. It's a combination of several instantaneous velocities, right? Like for instance, if you were looking at a graph that looks like this, right? And let's say that this is, representing the velocity of some kind of projectile or some kind of particle over some unit time, right? You can find the instantaneous velocities by finding tangents to the graph. Okay. Sorry, this should be position. This is the movement of an object. Sorry about that. Let's say this is the position of the object and this is per unit time. You can find the instantaneous velocity by drawing tangents to the graph. And I'll show you guys this as we go on throughout this lecture here. But the average velocity is between 2 points on the graph, which we draw a secant through. But you can imagine that each of these tangents that make up the secant can be used to approximate the average velocity if you average all of the tangents out, right? One thing that we do need to consider here is this notion of uniform motion. The uniform motion just states that the instantaneous velocity is 0, right? If the instantaneous velocity, if the instantaneous velocity is constant, not 0. Sorry guys, making a lot of mistakes today. If the instantaneous velocity is constant, okay? Now you can imagine that the average velocity is basically the average of the sum of the average of the instantaneous velocities present, right? So if you have the sum of all the instantaneous velocities and you're dividing it by n number of instantaneous velocities, you can find the average, right? It's just like if you have 5 instantaneous velocities, you add all 5 of them out, and then you divide it, you're just taking the average of all the instantaneous velocities. In the case where the instantaneous velocity is constant, then the average velocity will also be constant. This is an example of uniform motion. The uniform motion is when velocity in general, the average velocity, is constant. We'll take a look at some of these cases. It's very difficult to actually perceive something that is completely undergoing uniform motion because of the fact that there will always be some kind of force acting on those objects. If we're looking at just in everyday motion, I think the most common type of force that you would see being applied to moving objects is friction, right? There's always force applied to it. There's really no frictionless surface, or it's very unlikely that you would see an object undergoing complete uniform motion, but it's something that we want to consider, right? Okay, so a few things we discussed here was we talked about speed, which is the scalar of velocity, and velocity is defined as the rate of change of displacement or rate of change of position, because displacement is the change in position. And we also looked at that velocity has 2 different segments. We can look at instantaneous velocity or we can look at average velocity. The difference between instantaneous and average velocity is that instantaneous velocity occurs at a single instant in time. That means there is no interval. That means the interval is 0. And the average velocity occurs over an interval in time. Okay, so that's something that you want to consider. Now, what's really important is that we need to understand the relationship between position and velocity. And the best way to really represent that is through these position time graphs. Now, this is very important, guys. It's really just putting together how objects move per unit time. So if we look at some of the data here, take a look at table 1. So this is some data regarding some particle moving a certain position or certain distance per unit time. Okay, and you can notice here that this data is being graphed on this graph, and this graph is called the position time graph. I'm going to call it a DT graph, right? You might also hear of it as a PT graph, but for the most part, we'll use D for position. Okay, the position time graph. You can imagine that if you look at this graph, guys, on the y-axis you have a direction. Okay, so what this is saying is that as the y value increases, that represents the object moving south. Now, if you had more of a Cartesian plane here, you can imagine that the graph will not go this way because time has to be greater or equal to 0. There's no such thing as negative time. If you have position on the negative axis, like if this was like negative 200 meters south is like saying 200 meters north. Okay, so think about that. A lot of students get confused with graphs, but you got to imagine that directions are relative to each other, right? If you say that south is positive, then north is negative, right? Or if you mixed it up, then it would be vice versa, right? So in this case, you can notice that this graph illustrates a linear type of a relation, right? And what that's saying here is that for every 60-second interval, the object will cover the same amount of distance, right? So if you look at this, graph, this position time graph, every 60 seconds, it seems like the object is moving 330 meters south. And if you wanted to look at the velocity of this graph, right, the average velocity from 0 to 180, you're basically looking at this point to this point, right? You're looking at the secant from this point to this point. Now, you can actually imagine because this graph is linear, the secant will be equal to the tangent. Something that you need to understand is that the slope of the position time graph will represent the velocity. If you wanted to find the velocity, all you have to do, if it's a line, right, the instantaneous velocity will be equal to the average velocity. And basically, we'll call it v in general, right? And the velocity really is the slope of this graph. And what you can do is you could just use the equation y2 minus y1 over x2 minus x1, or rise over run, because this is a linear relation. You pick 2 points and you determine the graph, right? Or what you could do is you could just use the coordinates here that were given, right? So if you did find the slope here, you could do 330 minus 0 over 60 minus 0. And you can notice here that this value is basically 5.5. Okay, now if you look at this equation, literally this is delta D over delta T. Now the reason that we can subtract these values is because they have the same dimension, right? What we're essentially doing, the final position here is, you can write it as, let's say we're looking at these 2 points, right? So let's say this is final, this is initial. The final position here is 330 meters south. The initial position here is 0 meters south. And we know that displacement, because it's the same dimension, it's still south, we just subtract it. It's 330 meters south. Okay, so this makes it a lot easier for us, but it's technically the slope equation, right? So that's the proof regarding why that the velocity is the slope of the position time graph. Now, not all cases will look like this, right? This is a very simplistic example, but because in this case you have a line, the slope will be constant at any point, right? So here's what I mean by having some sort of uniform motion, like we talked about before. If I draw tangents to this graph, tangents will have the same slope as the secant, right? A secant is a line between 2 points on a graph. A tangent is a line that intersects 1 point on a graph, right? It only hits 1 point, and you can imagine that the slope of the secant is equal to the slope of the tangent here. because the slope of the secant is equal to the slope of the tangent, the instantaneous velocity is equal to the average velocity. And this is an example of uniform motion. Okay, so this is something that you want to understand. And as a result, if you convert this value that we discovered here, and you can notice that because the numerator was meters and the denominator was seconds, right, you're going to get 5.5 meters per second, right? And that value will not change. So as a result, the velocity time graph that you can see here in right, this velocity time graph is going to have a horizontal line, right? You can imagine that this basically means that the object is moving from 0 to 180 seconds. It's going 5.5 meters per second south. Okay, so it's very important that you can convert between your position time graph and your velocity time graph. And you can also notice that this is an upward sloping line. So what that means, having this positive sloping line, it means that the object is going to constantly move south, right? Let's take a look at this example here, right? If you look at this example of this line, and we take a few points here, right? Let's just say that we don't have any units here, right? Let's just take 2 of these points, right? And I'm just going to use rise or run because we're given a grid system here, right? This is 2 meters west. This is 3 seconds, right? And you can almost imagine that it's rise over run. Now I don't know what units these are going up by, right? But you can imagine that this is 2 over 3 units. It's meters per second. But the key idea here is that this has a negative slope. Okay, we're not given units, so I can't really do the calculation, but you would find the slope and then you would graph it here. This is going to also be uniform motion. But what the key idea about this is that if you look at the y-axis, this is the position that's going west, right? Because this is a negatively sloping line, the object isn't heading west, it's heading east. And that's what you see a conversion here, right? If you wanted to represent the velocity going east, this is a positive line. If you wanted to represent the velocity going west, then you would have to draw it here somewhere, right? We don't know exactly what this value is going to be, but we would draw it there somewhere, okay? And this basically, well, maybe I'll use a different color so that way you can see it, right? But then the graph would end up here if this was going west, right? It would be below the x-axis, okay? So make sure you guys really look at the direction of the graph, right? The direction is just associated with what your reference direction is. If you say that west is positive, then east is negative. If you say that east is positive, west is negative. So just make sure you do that conversion between the graphs. Okay, but the very key idea here is listed here, right? But you have to always remember that these are vector quantities that you're working with. Okay, so we mentioned that this is an example of uniform motion, and this is indicative of a horizontal velocity time graph. Okay, hopefully you guys understand that. Now, in actuality, we're not going to have too many cases of uniform motion because of the fact that there's always forces at work. And basically, this is a more realistic graph. Okay, so I have a table of values here. I have a graph. So this basically is a graph of those the position of a particle per unit time, right? And you can notice that the graph is not linear. So this means that the changes are going to be different for each case. And this could be very easily demonstrated by drawing tangents to these points. So for instance, we know that the slope of any kind of position time graph will give us velocity. If we wanted to find the instantaneous velocity, we would draw tangents to these points. Okay, so this would be the instantaneous velocity at time 1. This would be the instantaneous velocity at time 2, instantaneous velocity at time 3, instantaneous velocity at time 4. And you can notice that the slopes of the instantaneous velocities are increasing, right? So that means that the object, in essence, is going faster and faster. It's essentially speeding up, right? The average velocity is basically demonstrated by drawing a secant, which I'll draw in green, let's say we want to look at the average velocity between this time interval, between 0 and 8 seconds, right? Then you would draw a secant between this point and this point. Right? And you would find the slope of the secant. So the slope of the secant would give you the average velocity, but the slope of the tangents would give you the instantaneous velocity. So this is, you can notice that the average velocity is supposed to be the average of the instantaneous velocities if you wanted to calculate it accurately. Depending on how many instantaneous velocities or how many tangents you draw, the more tangents you draw, the more accurate your value is, right? That's where we teach you guys calculus to kind of do this without actually having to draw tangents. But if you haven't taken calculus, don't worry, you're not at a disadvantage in this course. For the most part, we're just going to be looking at certain concepts, and we'll always find ways around calculating instantaneous values by drawing graphs and so forth. Okay, so don't worry too much about that. And you can imagine here that the instantaneous velocity, so I was going to change colors. If you add up all the instantaneous velocities, say you add all of the instantaneous velocities, and you divide by the number of instantaneous velocities you added, then you could find the average velocity, right? So that's basically, or you could just say find the average of the instantaneous velocities, average of instantaneous velocities. You can find the average velocity, but you can notice here that in both cases, the object is speeding up, okay? So in this scenario, you're going to have an object that is going to constantly be changing its velocity, unlike what we looked at before, and this is non-uniform motion. Okay, and we'll talk about this concept in the next slide. But in essence, a lot of particles, most particles, will not have uniform motion. It's because uniform motion is more of an ideal scenario. Okay, so a few things, a few take-homes here, guys. Slope of the tangent of a position time graph gives you the instantaneous velocity. A tangent is a line that only hits one point of the graph, right? But the slope of a secant is basically the average velocity, and it's between an interval. Okay, so these are two things that I really need you to understand, and I've kind of demonstrated that here. There is a tangent at each of these points, and there's also a secant that is demonstrated in different colors, right? But you can also see that what we just illustrated there. This you don't need to know this formula too much, but it's basically what we were talking about before. This is basically for the instantaneous velocity, guys. But we're not going to be using this formula. I'm just kind of illustrating that the instantaneous velocity occurs at a single instant or when the time interval approaches 0. That's essentially what it's saying. Okay, so keep this in mind. It's very important to understand also the direction associated with that. So, never lose sight of that. Okay, so you can go through this. And like we mentioned before in the previous slide, I guess if you guys look back on it, you can notice that the instantaneous velocities are changing, they're increasing. And this notion of increasing or changing velocity is known as acceleration. Okay, acceleration is defined as the rate of change of velocity. Like velocity, because velocity has average and instantaneous states, so does acceleration, right? So acceleration in general, average acceleration is the change in velocity over change in time. Because change in velocity is a state function, we would look at it as final minus initial over final time minus initial time. Okay, so that's basically the equation here, right? For the instantaneous acceleration, guys, we don't really look at this, right? But once again, you can take a look at this. Now there is another function that looks at the changes of acceleration, and it's called the jerk function. It's called, I don't make up these names. That's what it's called. The jerk function is basically the rate of change of acceleration per unit time. You don't need to understand this now. Maybe if you consider continuing with physics in the university level, you can look at how fast and slow something accelerates, It's not too important for our discussion, okay? But the instantaneous acceleration is basically the same formula, except now what we're doing is we're letting the time interval approach 0, okay? You don't need to know this too much, right? Key ideas out of this is that acceleration is the change in velocity. So in that sense, if you have uniform motion, which was defined as having a velocity that is constant, right? And another way to represent that is the instantaneous velocity is equal to the average velocity, right? If the velocity is constant, then the acceleration is 0. There is no acceleration because the velocity doesn't change, right? Uniform motion is unchanging velocity, right? So it could be an object that is at rest, or it's an object that is moving at a constant speed and direction, okay? So keep that in mind. Now, in terms of the units for acceleration, guys, if you look at the formula for this, for average acceleration, which is basically this, and you know this is average acceleration because you do have a time interval located here. If you look at the formula, velocity is measured in meters per second, time is measured in seconds. So it's like me doing meters per second divided by seconds, right? This is what we call dimensional analysis. You can multiply and divide units. You can do operations with the units the same way you could do it with algebraic terms or numbers, right? In this case, you get meters per second squared. Another way to write this, you could write it like this, ms negative 2, right? Negative 2, negative exponents, you know that. It appears on the denominator. So you might see it also like that, but just to give you a heads up, very important that you look at writing units, guys. Make sure you show your work. You don't per se have to write units in your calculation, but I would recommend it. Like I said before, what I'm really looking for, I don't care about your answer too much. What I'm really looking for is the procedure. I need you to show as many steps as possible. In the case that you do the right steps and you had a calculation error, I'm only taking 0.5 for the wrong answer. If the question's out of 4, you're still going to get 3.5 out of 4 if you do all of the steps and you show me all your work. So the way, and I think we discussed this for the last lecture, but the way that you want to organize or format your answers, I want you to use the graphs method, right? This is going to be the easiest way that I can possibly give you as many marks as I possibly can, because this is a very great way of organizing information, right? So this is the given, the required, analysis, solution. If you don't know how to use this method, just go back to the previous lecture or back to the previous PowerPoint slides and just do a quick review of this, okay? All right. So now we're going to look at velocity time graphs. And velocity time graphs are just basically the velocity or the rate of change of position of an object that is graphed per unit time. Okay, so if you look at this graph here, you can notice that this particle or this object is moving at this specific velocity at a certain time. And you can imagine here that if you look at each of these time intervals, right, that it seems like the object's velocity is increasing. Okay, so try not to mistake this for position, guys. Make sure you look at the units. But in this scenario, you can notice that the velocities are increasing. You can see this from the table if you need to look at the points. It's very hard to see through the units here. Right, so at time 0, the object was at rest, right? And when the velocity is 0, the object's at rest. At time 1 second, velocity is 4 meters per second. And these are all instantaneous velocities, so that's essentially what these are, okay? You can call this V1, you can call this V3, because this is velocity at time 3 seconds, V5, V7, right? These are all instantaneous velocities, but you can imagine here that the object is in fact speeding up, right? And the object is speeding up in the eastward fashion, right? So if you see a positive velocity and on the y-axis you see that the direction is east, then that means that the object is moving east. If you would see a negative velocity, so if the object, instead of the graph looking like that, right, if you saw something like this is meters per second east, and the object was moving like that, then that means that the object is moving west or negative east. Okay, so the slope of the graph, if the line is upward or downward sloping, or if the secant is upward or downward sloping, that just indicates the direction of travel of the object. Okay, so that's basically how we can describe it. And once again, guys, because we're looking at one dimension, so either we're looking at east and west or north and south, we're just right now looking at one-dimensional motion. Okay, it does become a little complicated when you add both dimensions on a time axis. So usually what we do on a graph, on a Cartesian plane, or even on a two-dimensional surface, we only tend to use a single dimension per unit time. Okay, so just keep that in mind. It's probably the easiest to look at that way. So these position time graphs, any type of time graphs that look at these vector quantities, we try to look at one-dimensional motion. So either north and south or east and west per unit time. Now, if you take a look at the velocity graph, and we describe the slope of a velocity time graph as acceleration because of the fact that the average velocity is the change in velocity over change in time, which is final velocity minus initial velocity over final time minus initial time. You can easily see that it's basically rise over run, right? So because if you take a look at these 2 points, right, this would be the final velocity, right? So this would be the final velocity, this would be the initial velocity, so this is change in velocity, right? And the direction is associated with east. This would be a final time, this would be a initial time, this is change in time. So basically the slope of these 2 segments is basically the acceleration, right? So the slope of the velocity function is acceleration, and in this case, rise over run is equal to slope, which is basically the equation that we looked at earlier, right? So that's basically the proof for why the slope of a velocity time graph is acceleration. And if you notice the slope of this graph, because it is a line, you should see a constant slope, right? But this constant slope can be graphed on this graph here, right? And this is your acceleration time graph, right? So we'll call this the AT graph, right? And in this case, if we want to calculate the slope here, you could just take any 2 points because it is a line that is constant. And in this case, let's say we take these points here, right? So the points are 3 and 0 and 12, and 5 and 0 and 20, right? This is velocity, and I'm graphing it as time. So it's time and velocity. Time is the independent variable, velocity is the dependent variable, and the acceleration here, the average acceleration, is basically 20 minus 12 over 5 minus 3, which is 8 over 2, which is 4. Okay, so you should see, did I make a mistake there? Oh, 1 second. Why did they write 8 here? The 20 divided by 20 minus 12, 8. That's weird. Maybe I used a wrong graph here. Who knows? But you should see that the acceleration should be constant, right? So it should have been 4. I don't know why it's saying it's 8. 12. Yeah. Okay, I guess I used the wrong graph, guys. Sorry. But in this case, you should see a constant line. Okay, so this should be 4, not 8. Right? There's a little typo there. Right, but this is just saying that the acceleration here is 4 meters per second squared, and the object is going east. Okay, so hopefully you guys understand that. Now, the other thing that you need to really understand, and something that we should kind of also discuss, is if we go back to our velocity time graph located here, right, the area under a velocity time graph is basically the displacement within that interval, right? Because you can understand that if you have a velocity time graph, because average velocity is change in position or change in or displacement over time, which is change in position, displacement, if you tweak around the equation, is basically average velocity times time. And this works with this works really well with really constant velocities such as this, right? So for instance, if you wanted to find the displacement between 0 and 180 seconds, all you have to do here is just multiply or just find the area underneath the graph. Right, so the area here would be 0 to 180, so it's 180 here. Just make sure you watch the units. And this is your average velocity. It's 5 meters per second. And the total displacement, so the total change in position between this time interval is 180 times 5, right? So that's going to give you 900 meters. This is something that you want to understand, right? So going back to this, because we know that average acceleration is change in velocity over change in time, if you wanted to find the change in velocity, you could just take your average acceleration and multiply by time. So in essence, the area underneath the average acceleration curve, or the area underneath an acceleration time graph, is in fact your change in velocity. And they're basically talking about that. They mentioned that below here, right? So the area beneath each segment of the acceleration time plot is the change in velocity during that time interval, right? Now this was a very straightforward example because the acceleration is constant. The case where you have constant acceleration, guys, it's something called uniformly accelerated motion. We'll get to this actually in our next few topics. Right, so uniformly accelerated motion occurs where the average acceleration is constant. We'll use K for a constant, okay? And I'm going to abbreviate it as UAM, uniformly accelerated motion, just because this is really a mouthful to say. And in the case where you don't have uniformly accelerated motion, if the acceleration changes between different time intervals, like something like this. So if you look at this graph, between 1 and, sorry, it wasn't straight enough. Between 1 and, or between 0 and 3 seconds, right, this was your acceleration. So the area underneath that portion of the graph is going to represent the velocity between 0 to 3 seconds of the particle, right? And you can notice that between 3 and 5 seconds, you had this, right? And that's saying that the object is speeding up at a lower rate between 3 and 5 seconds, and the velocity between 3 and 5 seconds is basically the area underneath that portion, right? And in this case, between 5 and 9 seconds, this time interval, right, the velocity, the area underneath that graph at that portion is the velocity between 5 and 9 seconds. Okay, so make sure you understand this. You can kind of gauge how fast or slow the object is moving, right? And if you did want to add all of those together, right, this total area tells us is 24 meters per second, right? And what you could do is using this, you could find the average velocity of the object if you really wanted to, right? You could just take these values, divide by 3, right? But for the most part, it's really useful for us to understand just how fast or slow an object is moving at certain increments in time. And you got to understand that not all velocity is going to be uniform like this. Well, this is an example of uniform motion because you have acceleration, but not all velocity will be constant like this, where the object is accelerating at a constant rate, right? Sometimes objects will accelerate at random rates. So this is an example of non-uniformly accelerated motion. Let me just clean that up a little bit, sorry. Right, and it does make calculations a lot more difficult when you have non-UAM or non-uniformly accelerated motion, right? But a lot of things in reality don't really follow an ideal scenario, right? But we do illustrate ideal scenarios because we try to model events to the best of our abilities, okay? So remember that we are doing these modelings because of the fact that we want to make predictions. And that's I think that's the key point of all aspects of science, or all facets of science, really. So if you guys take a look at slide number 8 here, here's another example of a velocity time graph. And you can imagine that this one is much less ideal, right? And this is more something that's a little bit more realistic. You can see that the curve or in this case, the line, it has different slopes at different intervals, right? And the slopes of those lines can be represented as the acceleration at those instances, right? And we can also understand, like we mentioned earlier, that the area beneath each line in the velocity time graph will also represent the displacement at the time. Okay, so I think I mentioned that earlier before I look at the acceleration time graph, but the key things that I want you to really get right now is that the area underneath velocity time graph, a VT graph, is basically displacement between a particular interval that you're looking at, and the area underneath acceleration time graph, an AT graph, say VT here. So the area underneath an acceleration time graph is basically the velocity or the change in velocity between a particular interval. Okay, so that's something that you really want to consider. So in this case, they gave us a velocity time graph. This area, we'll call this, I think they're calling it area 4 and area 5. This area represents the displacement from 0 to 3 seconds. It's basically how much did the object's position change from 0 to 3 seconds. This displacement here from 3 to 5 is the area from the area of the graph under 3 to 5 seconds, and it tells you the displacement of the object between 3 and 5 seconds. Right? In some cases, you might get funky shapes. You might have to break it down. So you got to find the area of the triangle first, plus the area of the rectangle below it. Right? And they kind of showed you an example of this, and you can go through this, guys. This is really the summary points. Now, what I really want you to understand is how does direction apply, or how does direction kind of integrate with this idea? Okay. So in this case, if you take a look at figure 10 here, it's the acceleration time graph of a football lineman being pushed from initial velocity of 0 by other players. Draw the corresponding velocity time graph. We're given the acceleration time graph here, guys. We know that the area below the acceleration time graph gives us the velocity time graph. And if you guys forget, you can just take the equation and rearrange it, and you can notice here that the change in velocity is average acceleration times that time interval. And this is the velocity at that particular time interval, right? So that's just the really useful way that you can understand a lot of things just by having the formula memorized, right? Because once again, these formulas are manifestations of observations, right? So in this case, what you want to do here is you want to find the area of each segment, right? We'll call this area 1, right? This is area 2. This is area 3, right? Now, because area 2, you can notice that the acceleration is 0, the object's velocity didn't change, right? So because the object's velocity didn't change, this is basically going to be constant. Now, in this case, if you're looking at the velocity, we'll call this 1, we'll call this 2, we'll call this 3. Velocity 1 here is basically 1 meter per second. So you're just finding the area. You're just doing length times width times 1, right? So this is 1 meter per second squared times 1 second, which is basically 1 meter per second. Okay, so that's V1, right? For V2 here, it's basically going to be 0. Right, so it's basically, this is telling us that you're just adding to this point. Right? Because acceleration is 0, there hasn't been any change in the velocity. So the velocity is still going to remain at 1 meter per second. Okay, so that's the idea. And V3 here, or area 3, we'll think about this as area 3, actually. That's fine, same thing. Okay, so this is area 1, area 2, area 3. The change in velocity here, but because you can notice that this is below the x-axis, right? And the distance here is, it looks like 2.5 to 4. This is 1.5. This is negative 0.5. This is basically 1.5 negative 1.5 meters per second. Clean that up. Negative 1.5 meters per second squared times 0.5 seconds. And you can notice that you should get negative 0.75 meters per second. Okay, now if you want to find, if you want to draw a corresponding velocity time graph for this scenario, what you want to do here is you need to find, you need to draw it for each of these intervals. Okay, so if you're drawing for each of these intervals, between 0 and 1 second, let's say that this is velocity meters per second east. You have, this is 1 meter per second, right? So what that means is you're going 1 meter per second from this point. Okay, so remember that you have to correlate the slope with the acceleration, right? And basically the acceleration doesn't change here. Let me see this. So acceleration doesn't change here, so the velocity will be constant, right? So the velocity will be 0. It'll be constant. So it'll still remain at 1 meter per second, guys. And in step 3 here, you need to show that it is a constant 0.75. So it's basically going down 0.75 meters per second. So you're going to show it like that. Okay. So remember that the negative acceleration means that you're going in the opposite direction, and you'll see that with the negative velocity. Okay, so this is basically how you would construct your velocity time graph. We'll do some more samples as we progress, but it's something that you want to really understand, okay? So let's go to the next slide. So I just kind of wrote out some key ideas here. We just need to understand that the time graphs that you really need to understand are the position time graph, the velocity time graph, the relationship between the position time graph and the velocity time graph. The slope of the position time graph is the velocity time graph. And you also need to know the relationship between the velocity time graph and the acceleration time graph. The slope of the velocity time graph is the acceleration time graph. And also you need to understand that the area underneath the velocity time graph is the displacement for a particular interval, and the area underneath the acceleration time graph represents the velocity for a specific interval. So these are just key ideas that I really need you to understand, so that way you can just kind of put that together, okay? So we did that. And I have a series of questions that you guys can give it, you guys can try. Hopefully, once you've given this a shot, we can also take it up. So that way you can kind of understand how to go about things. So I think we'll stop there, and then we will continue forward. Okay, so let's take a look at some of these questions just to kind of go over it. Let's take a look at 15C here. And in 15C, they want you to take this information, generate a corresponding velocity time graph. Well, the way you're going to look at a velocity time graph is you need to find the slope of the position time graph. So you need to find it. Let's look at each interval here. Right, so this makes it a lot straightforward. This makes it very straightforward because of the fact that you can imagine that the position is changing in a linear relation type of view. So in essence, the slope for any 2 points on that linear relation is going to be constant, right? So the slope between this point and this point, between 0 and 4 seconds, if we do rise over run here, it looks like we're going from 50 to negative 50, right, centimeters, right? So that's a distance of negative 100 centimeters. And the time interval here is 4 hours, right? So the slope of this segment here in your velocity time graph is negative 100 centimeters over 4 hours, which is basically negative 25 centimeters per hour. That's your unit, right? Now, if you looked at drawing or constructing a velocity time graph, let's say that we kept the dimension or the dimension the same, right? So if this is your velocity time graph, if we kept the direction the same, right, meters per second, and this is going south, because it's going south, uh, we can imagine that because it's a negatively sloping line, the object is moving north. So because we have a negatively sloping line and the object is moving north, the velocity should appear down here. Okay, and this value here would be negative 25, right? And it's just going to be a horizontal line because that implies that the velocity is constant from 0 to 4 seconds, right? So this is 4 seconds, 0 seconds, right? You guys can do this on grid paper, but I'm just kind of drawing a sketch out for you. Okay, so that's between 0 and 4 seconds. And then for the next step here, you can see that this is a positively sloping line, right? So a positively sloping line just means that according to this graph, the positive direction is south, so the object is now moving south again, right? So if the object is moving south, what we need to do, let's find the velocity here. Once again, this should be constant because we have a line. And the distance between this on the vertical axis between 100 and 150, this is 150 centimeters. Distance between 4 and 8, this is 4 hours. Right, so if we were trying to find the velocity here, right, we're going to do 150 centimeters over 4 hours. This should be positive. And if we calculate this out, I got 37.5 centimeters per hour. Okay, so it's really important to, sorry, this shouldn't be meters per second, guys. In this case, it's centimeters per hours. Really easy to make mistakes on this. Keep the units consistent. So this is going to be 37.5. So let's say that this is like somewhere here, right? Once again, I'm just drawing a sketch, guys. And you can notice that the graph should be above the positive axis. Okay, so it might look a little weird because of the fact that you have this missing gap here, right? But that's essentially what's happening at this point, right? So you can see that there's a change in velocity at 4 seconds, and that's what this is indicating, right? I would not connect these points. I would just leave it the dotted lines, or you can just leave it as the horizontal lines, right? And that just implies that there is a change. So for the most part, it's pretty straightforward when you have constant velocity. However, if this graph was curved, such as something like this, right, in question 17, you have a position time graph that's actually a little bit more realistic. They want you to find the instantaneous velocities at 1, 2, 3, and 4 seconds, or in 5 seconds. If you have a graph that's curved and you want it to generate a velocity time graph, you need to actually find instantaneous velocities and graph them. Yeah, so it's a little bit more difficult. The much more inaccurate way of doing that is just generating a secant, but ideally we would say instantaneous velocities. Just to understand a little bit on instantaneous velocities, we said this was the slope of the tangent of the position time graph. They want you to find it at t is equal to 1 second. So 1 second looks like here, right? So you would just draw to the best of your ability a tangent, right? And this is basically, let's call it V1 for instantaneous velocity at time 1 or time 1 second, okay? At 2 seconds, right, this is your corresponding point, the velocity, the tangent could look like that. You can see it's negatively sloping, right? Now, technically, actually, sorry, this wouldn't be negatively sloping. This is at the maximum. It looks like it's the maximum. So usually maximum minimum points, guys, the tangent is actually going to be, the slope of the tangent will be 0. Okay, that's what it seems like you're doing here in this position. It's just saying that the maximum point, which looks like the peak of the graph, the furthest the person or the object has moved is 15 meters east. Okay, so that's the maximum point. I'm assuming this is some sort of pendulum or some kind of object that is oscillating. So oscillating means that it's going to have a periodic motion or a repeating motion. Okay, so a pendulum has a repeating motion. There's a certain maximum distance that it can move in a certain direction, and there's also a minimum distance that it can move in a certain direction. Okay, and the minimum distance is shown here. Maximum distances are shown here. Okay, you guys are probably wondering, okay, why is this this vertex here considered a maximum? Well, you got to imagine that in terms of negative and positive, in terms of position, it's just associated with direction. So the maximum position looks like, 15 meters east, and the minimum position looks like 15 meters west. Okay, so you kind of have to change your worldview from negative and positive to associating it with direction. Okay. Anyways, the maximum and the minimum at points of extrema, which include a maximum and minimum, the slope of a tangent is always equal to 0. So that's something that you want to understand, right? And you may have seen this also in other courses like advanced functions or calculus. And basically, you can imagine that the slopes are changing, right? So this is, let's call this V2, and the slope of V2 here for the instantaneous velocity at t is equal to 2 seconds is 0 meters per second, right? And they also asked us to find what is the slope at 3 seconds. Well, 3 seconds is here. This is another tangent, and once again, you need to draw a tangent out, sketch it, and then find the slope of that tangent, right? And you can imagine, because you're sketching these things, it's not going to be accurate. Luckily for us, we do have a stream of mathematics. We have calculus to calculate this for us. Okay, but don't worry too much about that. Right now, I just need you to understand that if you draw a tangent to a point on the curve and you find the slope of that tangent, that'll tell you what the instantaneous velocity is, if it's a position time graph. Okay. And they also asked us 4 and 5 seconds. I'll just do 5 seconds, and I think you guys understand this, right? We can draw a tangent here, right? So you can imagine that these tangents are changing. In real world scenarios, tangents will always be changing because the motion itself is not going to be completely linear. So in this case, the velocity itself is not going to be linear. How you can construct your velocity time graph is you can basically plot the instantaneous velocities and then generate it, put it together. Okay. Another question that we should kind of take a look at. Question 18 is more related to vector addition. So hopefully you guys can review some of your vector components. Vector sum of displacements is associated with net displacement, right? So it's displacement 1 plus displacement 2 plus displacement 3 plus displacement 4. If you're approaching a question like this, break each vector down into a sum of its components and then add up the components, okay? Question 20 is associated with calculating, using some of these kinematic equations to solve for certain descriptions, so displacement or average velocity. Okay, so I think this would be a little worthwhile to take a look at. So let's take a look at question 20 here. I'm just going to erase some of this stuff. Hopefully I can use some of the space up here. Okay, so question 20 is stating, just going to see if I can change colors. So question 20 is stating that a skater on Ottawa's Rideau Canal travels in a straight line 8.5 times 10 to the power 2 meters that is going 25 degrees north of east. It does help us to draw these out, guys. So this is north, east, this is south, this is west. If it's going 25 degrees north of east, you start at east and you're going 25 degrees north. So it's basically going this way. So this is 25 degrees, right? And in essence, this is basically what we're given. So this is one of our givens, right? In essence, basically, the skater is going, this is a position of the skater. We'll call this D1. And what I'm doing is I'm trying to employ the grass method, right? So the position here is 8.5 times 10 to the power 2 meters, right? And this is going 25 degrees north of east, right? And we're also given that his second or her second position is 5.6 times 10 to the power 2 in a straight line. Okay, so 21 degrees east of north. Okay, so 21 degrees east of north, we'll just look at the vector quantity here. So we'll call this D1 actually. But I would really recommend using the grass method. So this is east 25 degrees north, right? It means the same thing. You can write it like that. Position 2 here is 5.6 times 10 to the power 2 meters. This is going 21 degrees east of north. So you're starting at north. Then you're going 21 degrees east. So you can write this as north 21 degrees east, right? And the entire motion takes 4.2 minutes. So delta t here is 4.2 minutes. What is the skater's displacement? Now, if you're looking at displacement, guys, you got to think about these vector quantities. Because they're two-dimensional, there's east and there's north, right? You can pretend this is x and this is y. You have to break it down into components. So that's really the first thing you need to do, right? So let's break it down into components because in this case, your r here is going to be displacement. And the second question here, the r in the second question for your grass method, it's going to be associated with velocity. So you can imagine that's already linked with question A here, right? So you're trying to find average velocity, right? Now, before I do that, I'm just going to break down my vectors into components, right? So to break it down into components, if you construct your graph, I'm just going to draw it a little bit bigger here. This is D1, right? And then you have D1y and D1x, and this was 25 degrees, right? And if you wanted to break it down into components, what you can really do here is you could use the sine and cosine ratios. So D1 can be written as, let's figure out what D1x and D1y is, right? So D1y is basically sine 25 times D1, which is 8.5 times 10 to the power 2. I'm just going to change it to 850 meters because it's easier, right? And D1x is basically, and you can imagine that these are both positive directions. And this is once again very arbitrary. I usually make east positive x, west negative x, north positive y, and south negative y, right? So D1x here is basically cosine 25 degrees times 850. So I'm just going to crunch this out. Try to keep your calculator in degrees, guys, because if you do have radians, the value will be off. 359.23. Clean that up a little bit. And this value here, you're doing cosine 25 times 850. So this is 770.362. Okay, and once you have that, you can imagine that your D1 vector here is going to be written as D1x and D1y, right? And I really want you to really master these component coordinates and get used to writing it this way. So 770.362 and 359.23. Okay. And that's basically D1. So this is one of your vectors that you're going to be using. Okay, you could do the same thing for the other vector. See if I have some space here. Let's just do it here or something. I'm going to make sure that for the next couple of slides, I'm going to get some room so I can kind of do these questions out better. But that's fine. This is the second vector we were looking at. This looks like 69 degrees, right? And in that case, this is east 69 degrees north, right? So because they're going in the same direction, oh, this was supposed to be, 21 degrees east of north. Okay, that's fine. So in that case, this is D2y, D2x. So you're doing the same thing here. So D2x, D2y. So this is equal to cosine 69 degrees times d2. d2 here is, looks like 560 meters, right? Because 5.6 times 10 to the power 2. And d2y here is sine 69 degrees times 560 meters. And I'm just going to crunch this out. So give me like a few minutes to do that. 560. So I got 200.686, right? Try to keep as many decimal places as you can for your calculations, guys. At least a minimum of 2 decimal places. We'll do significant digits at the very end. But you can notice that in the question, we have 2 significant digits, so your answer should have 2 significant digits. Okay, so that's something that you want to understand. And then the last one here was sine 69 times 560. So I got 522.805. Okay, so technically you can write this, you write D2 here as 522, whoops, as 200.686 and 522.805. Now you have D1 and D2, you need to find the scalar's displacement, right? Now we understand that displacement, this is where your analysis and solution comes in. Let me see if I can create a new space here. Give me 1 second, guys. Sorry. Okay, so I'm just going to clean this up. Let's just look at some of the values that we had. So our initial position vector, D1, we said could be represented as 770.362 and 359.23. And then our second position, we can call it initial and final position, guys, if you want to look at it that way. This is initial, this is final, same thing, right? You can call it D1 or DI, it doesn't matter. And D2, we said it was 200.682. Whoops. Let me just erase that. Well, it's not letting me go back to the other slide. Whoa, a lot of technical difficulties here. What happened there? Okay, so I'm just going to make some space here. Just having a little bit of issues. Whoops. So I'm just going to okay, so we have our 2 displacement vectors. And we have D1 and D2. And what I'm going to do now is I'm going to find the displacement. Okay, so I'm just going to erase all of this. Are you kidding me right now? Okay, so we had the initial velocity was 770.362 and 359.23. And the final velocity D2 here was 200.686 and 522.805. Right, and you can imagine that this is going to be in the form of east is positive x, west is negative x, whoops. Right, west is negative x, north is positive y, and south here is negative y. Okay, so you want to think of it like that, and we drew out the initial the directions associated with that, and when you write it in component form of this, you want to find the displacement. So this was what part 8 was asking us. It was, what is the scalar's displacement, right? And this is basically your analysis and the solution, which you can combine it together. This was what was given, right? And what you're trying to find for A here is you're trying to find displacement. And the displacement is the final, which is the second position minus the initial position, okay? So you're basically doing vector addition of your opposite vector of position 1. So your opposite vector of position 1 here is negative 770.362 and negative 359.23, right? And if you're adding this with D2, you're just adding the components together, right? So you're basically doing 200.686 minus 770.362 and 522.805 minus 359.23. Okay, this should be a 2 here. And if we calculate this, which is our displacement vector, we calculate this, should get, so I'm just going to get 200.686 minus 770.362. So I got negative 569.676 and 522.805 minus 359.23. So this is 163.575. Okay. Now, what does this information tell us? Well, this tells us that the displacement of this object is basically about 569.68 meters west, right? Because this is x, right? Negative east, right? Negative 569.676 east is 569.68 meters west, okay? So the displacement is 569.68 meters west, as well as positive 163.58 meters north. Okay, so that's really the idea. Now they want you to find the displacement. These are the two components of your displacement vector, right? So in your two components of your displacement vector, if you're going 569.68 meters west, you're going this way, right? So this is 569.68 meters west, and then you're going 163.58 meters north. So your displacement here should be somewhere there. So this is your displacement vector, right? And in order to find your displacement vector, you need to use Pythagorean theorem. Okay, so you would do 569.68 squared plus 163.58 squared, and that should give you the magnitude of your displacement. So I'm just going to crunch that in the calculator. It does take a little bit of time, guys, but you have to kind of get used to this. Okay, so I got 592.7 meters, right? So it's 592.7 meters, and basically, this is what your displacement will be. Okay, now, we got a different value there. Why is the value different? It's 1.3. It must have been a mistake or something. Yikes. Okay, you know what? I'm just going to redo this question. Don't worry about this right now then, because I think I messed up on the calculations. Man. Okay, so what we're going to do now is we're going to look at instances of uniformly accelerated motion. And one of the cases that we discussed last time was in one of the velocity time graphs, we had a linear velocity time graph. So the acceleration time graph looked like horizontal lines. And when the acceleration time graph is horizontal specifically, that's an indicator of uniformly accelerated motion. Okay, so uniformly accelerated motion just refers, and we're going to call it UAM for short, but this just kind of refers to acceleration that is constant. And what acceleration that is constant means is that the velocity is changing by constant increments. Okay, so let's take a look at this. So if uniformly accelerated motion exists, that means acceleration is held constant, right? And when acceleration is held constant, if you looked at an acceleration time graph, guys, it would look like a horizontal line. Okay, so this would be an example of uniformly accelerated motion, right? And maybe this was acceleration, meters per second squared. Maybe the object was going east, right? And this would be indicative if you were to compare this to its counterpart velocity time graph, which was meters per second going east, then basically the object would be following something similar to that. Okay, so you'd have a linear velocity, and as a result, you would have a constant acceleration. The instantaneous velocity, the instantaneous acceleration will also equal the average acceleration if you have uniformly accelerated motion. But I think the most important thing that this actually brings up, this is more of an ideal situation. In real life, in real world scenarios, you may not always see uniform accelerated motion, but there are very important applications of this, such as free fall, when an object is just falling under no other force except for gravity, right? So, if you're looking at an object falling in the sky with negligible air resistance, then the only force that's be acting on it would be gravity, and as a result, the object to some extent will basically feel uniformly accelerated motion. We'll talk about that afterwards when we talk about free fall. But the reason that this is so important is you can actually use a series of equations to describe uniformly accelerated motion. And these equations are called the Big Five equations. There's 5 of them. And this is kind of related to some of our descriptions of average velocity and average acceleration, right? So some of these descriptions that we talked about earlier. And these are some of the equations that you're going to be looking at. And you can take a look at this chart here. To look at which equation will help you to isolate which variable and so forth. I think this is a great way to organize this information. But throughout the most part, we're going to kind of look at this stuff by doing questions, okay? So uniformly accelerated motion has to be assumed when we're looking at these equations. And for the most part, guys, acceleration will be constant, okay? So let's take a look at a question. A badminton shuttle or birdie is struck, giving it a horizontal velocity of 73 meters per second west. Air resistance causes the constant acceleration of 18 meters per second east. Determine its velocity after 1.6 seconds. Okay, key idea about this, you got to look at uniformly accelerated motion separate for each dimension. Because we're only given east and west, right? If you think about your navigation rows or your Cartesian plane here, right? This is only going to affect one dimension, which specifically the x dimension, right? So we're going to start off by looking at these one-dimensional uniformly accelerated motions first, and then we'll go towards the two-dimensional examples, okay? So in these one-dimensional uniformly accelerated motion problems, you just have to consider that single component. In this case, it looks like it's our x component. And let's model this by looking at the grass method. So we're given here that the velocity of the birdie initially is 0 meters per second, because it says that a badminton shuttle or birdie is struck, giving it a horizontal velocity of 73 meters per second. Initially, before it's struck, we could say that it's at rest, okay? So the final velocity here seems to be 73 meters per second. Now you have to, because there is one-dimensional motion and there's two directions, let's say that east is positive, west is negative, right? So if this is negative and this is positive, right? You can write this as, if you're looking at just vectors, you can write this as as negative 73 and 0, right? The reason we're writing this as 0 is because the y component of this is 0 and the x component is negative 73. Now, if you just wanted to just look at the x component, you can just write it like this, and then as a result, you're just looking at this single value. So this is negative 73 meters per second, because we're saying that east is a positive direction. And so you can write it as a vector using the component form, or you can just look at the single component. That's what we're doing here, if you're just looking at a single value. Air resistance causes a constant acceleration of 18 meters per second squared. So the acceleration is constant. right? And you can think about this as average acceleration, guys, right? It's basically 18 meters per second squared. And that's one of the reasons between constant acceleration is that the instantaneous acceleration is equal to the average, okay, which is equal to some kind of value k, which is the constant. Now this is going east, so that's why I made it positive. You want to find its velocity after 1.6 seconds. So we're given the time interval here, it's 1.6 seconds. So now that we've written out our givens, we want to figure out our required value, or what we're trying to find, right? And what we're trying to find here is its velocity after 1.6 seconds, okay? So it seems like it's start giving it a horizontal velocity. Oh, okay, sorry. I think I need to change this because I think they're taking the initial point here as negative 73 meters per second. So we don't know what our final is then. Right? So they're taking the initial velocity, not from rest, but the initial velocity is the 73 meters per second. So once you hit the birdie, it's moving at 73 meters per second, but then the object should basically be slowing down due to air resistance. One thing you want to understand, guys, is that if the acceleration and velocity are opposite in direction, so if your acceleration and velocity are less than 0, the object is slowing down. Something that you want to understand. If the acceleration times the velocity is greater than 0, the object is speeding up. Okay, so basically the initial velocity is the birdie that's being hit by the badminton racket. And as the birdie is moving through the air, it's going to slow down due to the air. So that's the air resistance, which is 18 meters per second in the opposite direction. It's going east. So what we want to do is we want to find the final velocity. So if it's slowing down, then the final velocity should be lower than the initial, right? And this is one of the best things about organizing the data. So you can notice that when I made that realization, I could go back, I could change up some of the values by just organizing my values better, okay? So analysis and solution, you want to use the big five equations. We can use the big five because this tenet is true, right? And you want to figure out final velocity. You're given acceleration, given time. So it makes sense to use equation 1 here. So if I use equation 1, for the analysis portion, I can write down the equation. And because you're only applying this for the x dimension, I'm going to write this as v2x or vfx. v2 is vf. Doesn't matter what you call it. vix plus ax delta t. Right, you can notice that I took the same equation and I just represented it for one component. So something that you can understand is that you can write a vector of any vector equation to compose it to its components, right? Because a vector to an extent is the sum of its components. So if you are looking at the final velocity vector, make sure you put the appropriate negatives and positives. Negative 73 meters per second plus acceleration is 18 meters per second squared times time, which is 1.6 meters per second. Oh, sorry, 1.6 seconds, not meters per second. Sorry about that. And the final velocity on the x component here, if I crunch this out, is negative 44.2 meters per second. So what does that tell us, right? It's telling us that now the final velocity, therefore the velocity of the shuttle or birdie, whatever you want to call it, is 44.2 meters per second west after 1.6 seconds. So you can imagine that from where it started, from where it ended, the birdie slowed down. It makes sense because the air resistance is decelerating or reducing the speed of the birdie. Okay, so this is the power of these equations. Is really useful. You can find a lot of information based on that. But make sure that you make the appropriate signs, guys. You don't have to make east positive and west negative. I just tend to do this conventionally because I think about this as a Cartesian plane. This is positive for y and negative for y, right? So it's really up to you, but you just have to, in your final statement, you need to make sure you put the appropriate direction associated with it, right? Now, ideally, I wouldn't write this value as 44.2 because of the fact, and this is something that's very important that you could lose marks for potentially, but because the lowest number of significant digits in your question is 2, I would write my answer as 44 meters per second. Okay, so make sure you do incorporate the proper amount of significant digits at the very end. Right. Maybe I would advise you guys to use pencil to do these problem sets in the test and so forth, because in the off chance that you do make mistakes, you want to be able to correct it. So just kind of be vigilant on that. It's very easy to make mistakes. So that's the idea. Okay. Let's go do another question. Hopefully, we'll go through a few sample questions of one-dimensional motion. I think we'll end off with one-dimensional motion today. Maybe previous two-dimensional motion problems next time. But these equations are going to be key. Right? You always kind of have these equations with you. Just know how to use them and look at your parameters. That's one of the reasons why I really advise using the graphs method, and I want to see this in all your work, guys, because it will really help you to solve these problems. And if you do decide to pursue physics in higher level courses, maybe in the subsequent years, this will really come in handy. Okay, so a baseball traveling horizontally at 41 meters per second south is hit by a baseball bat, causes its velocity to be 47 meters per second north. The ball is in contact with the bat for 1.9 milliseconds and undergoes constant acceleration during this interval. What is the acceleration? Okay. So let's write our givens here. And when you guys are writing your givens, make sure that you maintain SI units, okay? So velocity should be measured in meters per second, right? Position should be measured in meters. Acceleration should be measured in meters per second squared. If you see other units, you got to do the conversion. Like if you see acceleration being measured in kilometers per hour squared, you got to convert it to meters per second squared, right? If you see velocity being measured in kilometers an hour, you got to convert it to meters per second. Right? And there's a few things you should kind of know, that an hour is 3,600 seconds, right? You know that there is 1,000 meters in 1 kilometer. And then going on from there, you have to kind of do dimensional analysis and do conversion factors and convert it into the other appropriate units. Okay. Anyways, what we're given here is that the baseball is traveling horizontally, right, at 41 meters per second south. Although south, it depends on what your reference point is, right? Most people think, okay, when you say horizontally, don't you mean x and x, just x, so east and west? Well, horizontally it's relative to the position of the person, right? If a person is north and south, then this would be their horizontal axes, right? So that's basically what it's saying. But this is once again, it's going to involve one dimension because you're looking at north and south. And in this case, because we're looking at north and south, we can use y here. So we're given that the initial velocity of the baseball, call it VI, y, is 41 meters per second. Now, because it's south, I'm going to say that north is positive y and south is negative y. Now, you don't have to do it this way, but I just conventionally like to look at up as positive and down as negative. So the initial velocity is negative 41 meters per second, is hit by a baseball bat, causing its velocity to be, this is your final velocity. Final velocity is 47 meters per second north. You don't have to write the direction, right? And the ball is in contact with the bat for 1.9 milliseconds. So a millisecond is 1,000th of a second, guys. So your time interval, final initial time, is 1.9 milliseconds, which is basically 1.9 times 10 to the power negative 3 seconds. Or you can write this as 0.0019 seconds. Okay. Now you can also employ scientific notation and do these calculations, or you can just change to a decimal in this case. It also tells us that it undergoes constant acceleration. So if acceleration is constant, the instantaneous acceleration is equal to average. So that means that we can use uniformly accelerated motion equations or the big five equations, okay? What am I trying to find here? I'm trying to find the average acceleration. Okay, so in this case, because you're given initial and final velocity, it's really the same thing. We're going to use equation 1, right? So you notice that by looking at your variables. And in this case, I'm going to use V2 is equal to V1 plus A delta T. And because you're applying this for your Y components only, V2Y or VFY, I'm calling V2 VF, it doesn't matter what you call it. VFY is equal to VIY plus AY delta T. You're solving for AY. So I'm going to move this to one side. Now you can plug in values and then do this you can do this simultaneously, moving the variables. But I like to create one equation first and then work with it. If you want to solve for AY, I'm going to divide this by delta T. Whatever I do to this side, I'm going to do to this side. Cancels out. So AY is equal to VFY minus VIY over delta T. And at this point, I can just plug in values. So your final velocity was positive 47 meters per second, minus your initial velocity was negative 41 meters per second because this was south, this was north. Your change in time here is 0.0019 seconds. So if I calculate this out, I get 88 meters per second over 0.0019 seconds, which looks like 46315.79. Now this value wouldn't be acceptable because if you look at your significant digits here, once again, there's 2 digits, guys. So there's 2 digits. I'm going to write this in scientific notation as 4.6 times 10 to the power, it looks like 4.6 times 10 to the power 1, 2, 3, 4 meters per second squared. Okay, so it's a pretty significant acceleration, right? It's because this is happening in a very short time interval. It's 1.9 milliseconds, which should look like that, right? But that's basically the idea behind it. Okay, so you want to put the right amount of significant digits at the very end. So make sure you do that. And that's really the idea behind it, right? So it's accelerating very quickly is what it's saying. So that means that its velocity is changing very quickly. Okay, all right. So let's take a look at another problem here. So once again, I'm going to have to, if I show you some samples, I really want you to kind of pick up a few things from these samples, specifically how I organize these questions. And you're going to have to get used to doing that as well. Okay, so let's take a look at another one-dimensional uniformly accelerated motion problem. And then I will be also sending you guys a problem set this week. The problem sets will count for marks, guys, so make sure you do it. It'll just be a series of questions that you can work on. So we'll talk about that throughout the week. Now, question 21. Upon leaving the starting block, a sprinter undergoes a constant acceleration of 2.3 meters per second forward for 3.6 seconds. Determine the sprinter's displacement and final velocity. Okay. So you're starting, the sprinter is starting on a starting block. Okay. So initially, because the sprinter is starting at the starting block, if you guys have seen relays, you know what this looks like. The initial velocity of the sprinter is 0 meters per second. Initially, they're at rest. Okay, I want to just use the x component because let's say that they're moving in one direction. They're not somehow flying or lifting off the ground, right? So if this is like the track, the sprinter is moving like that, right? As you can imagine him running. I can't really draw that, right? So they're sprinting this way, right? They're not somehow flying off the track, right? So we're going to look at the x dimension specifically. So this is 0 meters per second. And we have a constant acceleration, okay? And forward, let's say that we're looking at just like, maybe it's going in this direction. This is forward. Okay, so this is positive x, backward is negative x, right? Or you can think about this as east and west. It's really your call, right? So that's your initial velocity, and the time difference here is 3.6 seconds. And basically the acceleration, the average acceleration, which is constant, so this indicates that we can use UAM, is 2.3 meters per second squared. Okay, so far it seems like all of our units are basically in SI units. Now the first thing you want to find here is the displacement. Second thing you want to find here is the final velocity. Okay, so let's start with the displacement. If we're starting with the displacement here, if you're trying to find displacement, we're given initial velocity, we're given time, we're given acceleration. If we're not given final velocity, so I think the best formula that I can possibly use for that, it looks like equation 3, right? So I'm going to apply this equation, and that's what the analysis portion is, right? You don't have to write the actual equation. You can also write it in its component form, the component that you're applying to. As long as I see the equation at least once, then I'm sure that you guys understand what to use. So delta D is basically, whoops, I wrote that twice, sorry guys. V1 T plus 1/2 A delta T squared. But I'm applying this for my X component, right? So you can say VI X delta T and AX, just get rid of that. Whoops, what happened there? AX delta T squared. Okay, think about T as delta T, guys, same thing. And in this case, if you use this equation, I'm going to change colors here, but if you use this equation, guys, you can notice that the initial velocity is 0 meters per second. So all of this is 0 because 0 times delta t is 0. So this tells us that delta dx is 1/2 acceleration on the x component, delta t squared. And if we try to punch in the equation here, you have 1/2 2.3 meters per second squared, and delta t squared is 3.6 seconds squared. And you can actually notice that if you look at the units, I'm just going to slow this one down just a little bit so you can see what happens. We can see that you get 12.96 seconds squared. Okay, that's me squaring 3.6 seconds, right? You can notice that when you're multiplying these two together, seconds divided by seconds cancels out. So you're left with meters. So that tells you, that's another indicator that you're doing it correctly. So 0.5 times 2.3 times 12.96 gave me 14.904 meters. So that's their displacement in that 3.6 seconds, right? And because in your question you have 2 significant digits, because that's your lowest number of significant digits, I would round this to 15 meters. So the person's displacement, and what I want you to do is box your answers, guys. The person's displacement is 15 meters in 3.6 seconds. Now part B is asking us to find the person or the sprinter's final velocity. Let's do that here. Okay, so if we're finding the final velocity, which is Vfx, right, so what you're going to do here is you need to find the final velocity, but we're given initial, we're given acceleration and time. The easiest equation to use would be equation 1, right? You can use the other equations. They're all kind of derived from the same concept, but try to use the easiest equation available to you so you can save some time associated with that. So if you're trying to find final velocity, Vfx is equal to Vix, or initial velocity on the x component, plus acceleration on the x component, delta t, right? And because you know that this value here is 0, then your final velocity on the x component is basically acceleration, which was 2.3 meters per second squared, times delta t, which was 3.6 seconds, right? And you can imagine, once again, we can use dimensional analysis, guys. You take a look at this, multiplying this by 3.6 seconds, you're doing seconds squared over seconds, right? So if I move that to this side, if you think of it like that, if I put the 1 here, if you think of it like that, then your answer here, 2.3 times 3.6, I got 8.28 meters per second. So this is actually the units for velocity. So you can do operations with units, guys. That's called dimensional analysis. Really important stuff. And like I said before, 2 significant digits in the question, so your answer should be 8.3 meters per second. That's your final velocity. Okay, so hopefully you guys can understand this. The questions do get a little bit more challenging, so just try to go through the equations. I'm not really showing you I'm not really asking you to focus on really the question, but how I lay it out. The layout of the question, how I approach the question, how I organized it, that's something that you want to learn how to do so you can approach it. You can approach more complex questions. Okay. So hopefully you can try that yourself, but I will send you guys some questions so you have a chance to do that. So those were examples of one-dimensional motion. And one-dimensional motion just basically means we're looking at one set of dimensions. So it could be east and west, which would be the x dimension, or it could be north and south, which is the y dimension, right? This is positive y, negative y. This is positive x, negative x. However, we know that most motion that we're going to be looking at here is going to be two-dimensional, right? It's going to involve north, south, or east and west, right? Sorry, and east and west. So you can have combinations of all of these, right? So because of that case, it's very important to understand that we can only combine components that are the same. And we also need to understand that vectors can be written as a sum of their rectangular components, right? Like if you had a velocity vector, right, let's call this initial velocity vector, you can break that initial velocity vector down into its x component and its y component, right? Similarly, if you had an average acceleration vector, you can break that average acceleration vector down into its x component and its y component. All vectors can be broken down into a sum of its components, right? So you can also apply these formulas to either or component, but you have to do it separately. You can't combine x components with y components and vice versa. Okay, so let me give you an idea of how to use this, and try to remember your formulas from the previous case. Okay, so if we are taking a look at that, sorry, give me 1 second. If we are taking a look at that, a car with velocity of 25 meters per second east changes its velocity to 25 meters per second south, in 15 seconds. Calculate the car's average acceleration. Just to give you an idea of what this would look like. Right, we have an initial velocity here, guys. Right, the initial velocity is 25 meters per second east. Now, because you have initial and final, what you can do, because there's two dimensions, I would try to write this vector in component form like this. Okay, and the final velocity vector you can write in component form like this. Right, because basically every vector in two dimensions can be written as its two components, and you can add the two components up to get the vector, right? So if you wanted to write it that way, and if you visualize this, the initial velocity vector, guys, is 25 meters per second east. So this is the initial velocity vector. It's 25 meters per second. It's going east. This is north, west, and south, okay? And if you wanted to write it in terms of its component form, you would write it as 25 and 0. If it's just going east, there is no y component You can see that it's on the x-axis. Okay, and I'm going to say that east is positive and west is negative for the x-axis, and for the y-axis, north is positive and south is negative. Okay, and you can change it up. You can change up the directions, which one's positive, which one's negative. However, this is the way I want you to kind of approach it. Okay. Anyways, we know that the final velocity here is 25 meters per second south. So if it's 25 meters per second south, we're going 0 and negative 25 because I said south is negative. Okay, so what that means is VF, I use a different color for this so you guys can see it, it's going this way. That's VF. Okay, and this is also 25 meters per second. That's going south. Now, if you're trying to find, and we're also given the time aspect of this as well. We're given that time here is 15 seconds. So you can include all of this in your given section, guys, because that's all of the information you're given. You haven't really done much calculations associated with it. What you're trying to find here is the car's average acceleration. We're assuming that it's constant, okay? Well, you're given all these pieces of information. You think about what equation you use. Because we're given an initial and final velocity, we're given time, we could tend to use this equation. It's equation 1 if you look back on your previous slide. Right, but specifically, we're just going to apply this to our x and y components, right? Now, because we're given x and y components, if you wanted to do it collectively, you can combine these components by adding the components together, the way I did it this way. Okay, so what I'm going to be doing from here on out is you can imagine that this equation here, acceleration, we'll call this delta t. Right, acceleration times delta t is final velocity minus initial velocity. If you want to solve for acceleration, you're going to divide delta t to both cases. Now your vector component, and you can actually notice that this is in fact the velocity equation, guys. There's no surprise there, because the big 5 equations come from the generic kinematic equations. But this is what the equation looks like, right? And you can notice that for the denominator, it's just a scalar. We just have to plug in this 15 seconds. But for the numerator, it is actually vector addition, right? Well, specifically vector subtraction, right? So if we're doing vector subtraction here, vector, the final velocity vector minus the initial velocity vector, we can write this as the final velocity vector plus the negative initial velocity vector. Right? You're adding the opposite vector of the initial velocity vector. The negative initial velocity vector is basically negative 25 and 0. The final velocity vector is 0 and negative 25. If you're adding these two vectors together, and I would say review your component addition, right? If you're still having trouble, I will give you guys a link that you can take a look at, which will review component addition. But if you're adding these two together, if you're doing V plus negative VI, right, final plus negative initial, you basically have negative 25 and negative 25. Right? Well, what does that mean? Well, this is your y component, this is your x component. If you project it, if you look at doing the vector addition, you'll see it. Right? Now, you don't have to, for this one, you can actually just draw the triangle, but I would prefer you to learn how to do components for the other complex type questions. But technically, if you project it here, the resultant is that. Right? And you can notice that you have negative 25 here, positive 25 here, right? And this is positive 25. Sorry, 1 second. Oh no, yeah, negative 25 there. And, oh, sorry guys. I think there was this was final, oh, this is displacement, right? Okay. Negative VI here was negative 25, okay? Because we're finding the difference, okay? So because negative VI is here, then your displacement should end up here. Does that make sense? So you're not finding the net velocity, guys, you're finding displacement. right? So that just tells you the difference or the change in position, right? Because this is negative VI. And in this case, this is your resultant, which is your delta V vector. So that's what it should look like. Now, if you're finding the magnitude of this, right, the magnitude of this vector is basically the Pythagorean theorem. So think about this triangle here. It's a right angle, right? So you would do Pythagorean theorem. So this is 25 squared plus 25 squared. And that's going to give you, I punch down the calculator. This is just the magnitude. This gave me 35.3553, okay, meters per second. So that's the acceleration, right? So this is the magnitude of this value, right? And they just want you to find, first you want to find the magnitude, but then you got to find the angle associated with it. Okay, let's find the magnitude first. Okay, so let's just say we wanted to find the magnitude of the average acceleration. So we're just finding the total value here. Oh, sorry guys. Right, so we're just finding the total value there. So it's just 35.3553 meters per second over time, which is 15 seconds. Okay, and if you calculate this, 35.3553 divided by 15, I get 2.357 meters per second squared. If you rounded this off, you get, because there's two significant digits in the answer, in the question, excuse me, then the answer should have two significant digits. So this is 2.4 meters per second squared. That's the magnitude of the acceleration, but because it's a vector, you also need to find the angle. Now, in order to find the angle, if you take a look at this this graph here, or this diagram here, and I'm just going to make this a little bit bigger so you can see it. Right, this was negative VI, right, x, and basically this is negative VI, sorry. And this was VF, and this is your resultant. You're trying to find this angle. So if you wanted to find the angle of your resultant vector, think about this as west and south, then basically your angle here is tan inverse of the final over the initial velocities, right? So you're basically doing the tan inverse of, it looks like the initial was negative 25. Well, the final was 25, sorry. Negative 25 and 25. So it's negative 25 over negative 25, right? So you're basically finding the x and y components, okay? And in this case, you should get 1. So tan inverse of 1 should give you 45 degrees. Okay, so the direction is 45 degrees. Now, in terms of a 45-degree angle between a Cartesian plane, that's going to represent southwest. Okay, does that make sense? So this is the southwest direction. And you want to think about this as, this is your x component of your resultant vector. This is your y component of your resultant vector. Right, so this is delta Vx, this is delta Vy. That's essentially what we're doing here. This is delta Vy, this is delta Vx, okay? So that's essentially how you want to kind of look at this, right? And essentially it's 45 degrees. So this tells us that our direction here is southwest. Whenever it's south 45 degrees west or west 45 degrees south, or any direction that's 45 degrees to another direction, it's always the two directions together, right? Like north 45 degrees east is northeast, or east 45 degrees north is still northeast, okay? So this is basically our complete answer here, right? So your answer, your car's acceleration here would be 2.4 meters per second squared southwest, okay? So you can imagine the questions will get a little bit more complicated when you're looking at 2 dimensions opposed to 1, right? So you just kind of have to be able to examine each dimension separately by themselves and then kind of move forward with that in terms of the equations. So it does get a little complicated, guys, but you just need to kind of start by doing these questions and really learning the methodology behind doing the questions. Using the graphs method will really help you to do that. Okay, so I'm going to stop right there. What we're going to do, we'll take a look at some more two-dimensional problems for the next class regarding this. And this one's a little bit more complex question. I would ask you guys to do this question for homework. Just try it. So attempt this question, but then we'll take this question up for the next class, right? But I think that'll be all for today. So just make sure you kind of know some of these formulas. Just have them in front of you